lecture series on differential equations for undergraduate students. Today's lecture is in continuation of linear differential equations of second order. In last lecture, we had learned about these equations. Moreover, we have learned how to solve linear differential equation with constant coefficient of second order. We will learn something more about these equations. As well, we will also learn in today's lecture about non-homogeneous equations. So, first we will learn about the existence and uniqueness of the solution of initial value problem. Here we are not going to find out that is what are these conditions, rather we will state a result about under which conditions the solution of initial value problem does exist and under what circumstances that solution would be unique. So, the result here is existence and uniqueness theorem for initial value problem. If p x and q x are the continuous functions on some interval I and x naught is in I for differential equation y double dash plus p x y dash plus q x y is equal to 0 and two initial conditions, that is function y at x naught is k naught and the derivative of y at x naught is k 1, then this initial value problem has a unique solution y x on interval I. We have learned it that this solution, unique solution of this initial value problem is called the particular solution, and this particular solution we can obtain by giving a specific value to the general constants in the general solution. How we are obtaining those constant values for this particular solution? What we are doing is we are putting these initial conditions to the general solution and then find out the values for those constants. So, now we will learn that one. We had learned that general solution for second order equations contains two linearly independent solutions. Those two linearly independent solutions we are obtaining by some methods. We are checking that those solutions which we have obtained for the second order equation, whether they are independent or not. For that, either we had implied the basic definition of linear independence of function, or we had learned one more thing, that is those two solutions are not proportional. Today, we will learn something more about this linear independence of solution, which is known as Wronskian or Wronski determinant. What we do call the Wronskian? Wronskian for the second order equation y double dash p x y dash plus q x y is equal to 0. If it has two solutions y 1 and y 2, then the Wronskian of y 1 and y 2 is being given as a determinant whose first row contains y 1 and y 2, the two solutions, and the second row contains the derivative of those two solutions. Of course, we do know this is equal to y 1 y 2 dash minus y 1 dash y 2. This is called the Wronskian. And how we are checking the linear independence? If this Wronskian is not 0 for any value of x naught in the interval I, then we say on that interval I the two solutions y 1 and y 2 are linearly independent. Some more properties of this Wronskian. Given two functions f x and g x that are differentiable on some interval I, the Wronskian of f and g at some point x naught is not 0 for some x naught in I, then we call that f x and g x are linearly independent on I. Moreover, if f x and g x are linearly dependent on I, then this Wronskian of f and g would be 0 for all x in I. So, we see is that is if it is linearly dependent, we will get Wronskian of f and g to be 0 for all x, and if it is linearly independent, I could find out at x naught some x naught where it is not 0. Now, one special property which we are using for the differential equation, that is called Abel's theorem. What is that? if y1 and y2 are two solutions to the differential equation y double dash plus pxy dash plus qxy is equal to 0, then the Wronskian of the two solution is at some point x, that is w y1 y2 at x is equal to w y1 y2 at x naught into e to the power integral minus 0 to x px dx. We can show this result also. So, we are going to prove this. The differential equation y double dash plus py dash plus qy is equal to 0. We have been given that it has two solutions y1 and y2. Since these are two solutions, so they would satisfy our differential equation. What it says is that y double dash plus py1 dash plus qy1 is equal to 0 and y double dash plus py2 dash plus qy2 would be 0. Now, from these two equations, if I eliminate the term containing q, that is I would multiply the first equation by y2 and the second equation by y1 and subtract, then what we would get? We would get y2 double dash y1 minus y1 double dash y2 plus py2 dash y1 minus y1 dash y2 is equal to 0. Now, let us see what we have obtained. Again come back to our Wronskian. It is y1 y2, that is y1 y2 dash minus y1 dash y2. Now, if I differentiate this function, because this is a function of x, if I differentiate with respect to x, what I would get? y1 dash y2 dash plus y1 y2 double dash minus y1 dash y2 dash minus y1 double dash y2, that is y1 y2 double dash minus y1 double dash y2, since y1 dash y2 dash is getting cancelled it out. Now, we see what the equation we had obtained by eliminating q. We had obtained y2 double dash y1 minus y1 double dash y2 plus p times y1 y2 dash minus y2 y1 dash is equal to 0. Now, we see that the coefficient of p is nothing but the Wronskian, and what we are getting here, the constant term, that is nothing but the derivative of the Wronskian. Now, these are the function of x. So, we can write this equation as w dash plus p w is equal to 0, where w dash is the derivative of w with respect to x. That says is that we are getting a differential equation with respect to w. Now, what we are having is, now this is first order equation, we do know how to solve it. The solution of this is w x naught e to the power minus 0 to x integral p x dx. We do know that this solution we do know, and we do know this is what we have replaced w x naught as the constant which we are having, that we had replaced with a particular value x naught. How we could get this particular value? If I have been given the value of w at a particular value x naught. So, this is what we are getting as a solution, this we do know, that is what the Abel's theorem says. Now, from here what we are getting the result, that is if w at some x naught is not 0, I would get that w x will never be 0, since this whatever be this part, this will never be 0 for any value of x. That says is for linearly independent I require w x to be not 0 for only a single point, while when they are linearly dependent they would be 0 for all x. Now, let us see one example how we are using this Wronskian to find out the linear independence. Find the general solution of y double dash minus 2 y dash plus y is equal to 0. This is a linear differential equation with constant coefficients. We do know how to solve it. So, solution, let us see. What is the characteristic equation? That would be lambda square minus 2 lambda plus 1 is equal to 0. Now, we do know this is nothing but the lambda minus 1 whole square. So, I would get the double root lambda is equal to 1. We already know that the two solutions for this we are taking as e to the power x and x times e to the power x. Now, we want to check that these two solutions are linearly independent, and we would employ the method of Wronskian. So, we will find out the Wronski determinant for these two solutions. So, what it would be e to the power x, that is the first solution, then the second solution x times e to the power x, and in the second row the derivative of e to the power x, that is e to the power x, derivative of x times e to the power x, that is e to the power x plus x times e to the power x. If I calculate what is the value of this determinant, that would be e to the power 2x plus x times e to the power 2x minus x times e to the power 2x, that is equal to e to the power 2x, that is not 0 for any value of x. This says is that the two solution e to the power x and x times e to the power x, they are linearly independent. We know that we had already checked it using the method of constant proportion. So, if I take the ratio of e to the power x and x times e to the power x, that is coming out to be 1 by x, which is not a constant. So, this also we do know from the first method of knot proportion that they are linearly independent. So, what will be the general solution of this given equation? That would be C1 e to the power x plus C2 x times e to the power x. Now, we had learned about the linear independence by one more method, that is called Wronski determinant or Wronskian. Now, I will move to the non-homogeneous equations. So, first we will do non-homogeneous second order linear differential equations. What are they? We do know that they are second order linear differential equations with right hand side not to be 0, that is y double dash plus p x y dash plus q x y is equal to r x, and I should have that r x should not be 0. This we do. Now, we will learn about that is what we are going to solve this. So, what we say is one more term we are associating with this, that is corresponding homogeneous equation, where I will take the equation as such, but the right hand side as 0. This is called the corresponding homogeneous equation for this non-homogeneous equation, or sometimes it is also referred as associated homogeneous equation. So, this equation we are obtaining as the same equation, but the right hand side r x we have made it here 0. What we get one result, that suppose capital Y1 and capital Y2 are two solutions of non-homogeneous equation y double dash plus p x y dash plus q x y is equal to r x, and suppose small y1 and y2 are fundamental set of solution of corresponding homogeneous differential equation, that is y double dash plus p x y dash plus q x y is equal to 0. Here what we have taken, that is y1 and y2 are the fundamental set, that means they are linearly independent solution of this homogeneous equation. Then capital Y1 minus Y2 is also a solution of this homogeneous equation, and since it is a solution of this homogeneous equation, it can be written as a linear combination of the fundamental set of solution, that is y1 x and y2 x, that is I could write capital Y1 minus capital Y2 as C1 times Y1 plus C2 times Y2. Again, this is again a simple result which we can show here by the knowledge whatever we are knowing. So, let us prove it. Since y1x and y2x second derivative would be nothing but the second derivative of y1 minus second derivative of y2, and the derivative of y1 minus y2 is nothing but the derivative of y1 minus derivative of y2, will substitute this in our homogeneous equation, that is y double dash plus p x y dash plus q x y is equal to 0. Since we want to show that y1 minus y2 is a solution of the homogeneous equation, let us substitute it. What we do get, y1 double dash minus y2 double dash plus p times y1 dash minus y2 dash plus q times y1 minus y2. Now, rearrange the terms. First I write the terms corresponding to y1, that is y1 double dash plus px times y1 dash plus qx y1, then minus y2 dash y2 double dash plus px times y2 dash plus qx y2. Now, the first term which we are having, this is, since capital Y1 is the solution of non-homogeneous equation, that means this first terms what we are having, that would be equal to the right hand side of non-homogeneous equation, that is R x. Similarly, the second term will also be the non-homogeneous solution of non-homogeneous equation, that is, it should also be equal to R x. That says is R x minus R x will get 0. What it says, if I am substituting in this equation y1 minus y2, I am getting right hand side equal to 0. That says y1 minus y2 is satisfying this equation, which says that it is a solution. Now, since it is a solution, we can write it as a linear combination of the fundamental set of solutions, that is, I could write it as C1 y1 plus C2 y2 for some C1 and C2. Now, from here what we could get one more result. See what we could do. Let us say, let us consider the two solution y and ypx. What are they? They are actually, we are taking this non-homogeneous equation y double dash plus px y dash plus qx y is equal to R x, and let us say y is a general solution of this non-homogeneous equation and ypx is a particular solution of this non-homogeneous equation. So, now what we are getting? We are getting this as capital Y1 and this as capital Y2, the two solutions of non-homogeneous equation. Then by the previous result, we do know that y minus yp would be solution of corresponding homogeneous equation. Let us say that is the fundamental set of homogeneous equation, solution of homogeneous equation would be y small y1 and y2. That means, this would be equal to C1 y1 plus C2 y2. Now, from here I could write y as C1 y1 plus C2 y2 plus ypx. So, the first term C1 y1 x plus C2 y2 x is nothing but the general solution of the corresponding homogeneous equation, and ypx is a particular solution of the non-homogeneous equation. That says is the general solution of non-homogeneous equation yx, I can write as yhx plus ypx, where yhx is the solution of homogeneous equation, that is C1 y1 x plus C2 y2 x. This is the general solution of associated homogeneous equation, and ypx is a particular solution of the non-homogeneous equation. Thus, we are getting, now you see, we had already learned how to find out, or that is these solutions y1 and y2, they are linearly independent. Now, this yp which we are saying, if I am keeping this in the general solution, this yp should also be linearly independent of y1 and y2. So, this is important thing over here. Now, we come to our main theorem of non-homogeneous equation. This is about general solution. For a second order linear differential equation which is non-homogeneous, that is y double dash plus px y dash plus qx y is equal to R x. Its solution, general solution, can be given as general solution of associated homogeneous equation plus particular solution of the non-homogeneous equation, that is yx can be written as yhx plus ypx, where yhx is the general solution of corresponding homogeneous equation y double dash plus px y dash plus qx y is equal to 0, and ypx is a particular solution of our non-homogeneous equation. Now, what will be the particular result about the particular solution? The particular solution we do know can be obtained from the general solution yhx plus ypx by giving the specific values C1, C2 in the yhx. Since we do know that yHx is the general solution of associated homogeneous equation, ypx is a particular solution. So, it is not containing any arbitrary constants, the arbitrary constants are over here. Now, if I keep this C1 and C2 0, I will get only ypx, that is the particular solution which we are keeping over here, but that is not the only particular solution. We can obtain some other particular solutions as well by giving some values to the C1 and C2. So, what will happen to the initial value problem, that is from there we will obtain this C1 and C2 by putting the initial values in the general solution. So, the general solution of one more result over here, the general solution of non-homogeneous equations includes all solution. What this result says? This says if Px, Qx and Rx are continuous on some open interval I, then every solution of y double dash plus Px y dash plus Qx y is equal to Rx on I is obtained by giving suitable values to the arbitrary constants in general solution yHx plus ypx. That is, every solution of this non-homogeneous equation can be obtained through this general solution. It may imply there is no singular solution. Now, what we have drawn the practical conclusion out of these results? We have obtained that to solve a non-homogeneous equation y double dash plus Px y dash plus Qx y is equal to Rx, first R an initial value problem. What we do? First we do solve the homogeneous equation y double dash plus Px y dash plus Qx y is equal to 0 and find a particular solution yp of non-homogeneous equation, and then we do keep it over there. We had learned the techniques to solve homogeneous linear equations. Of course, there we have not done it for general Px and Qx, we have done only for the constants Px and Qx. That says this now. So, let us do first the examples we will do about this constant, then we will learn about functions as well. So, we do know if this constants, we do know how to solve this homogeneous equations, but the things remain is how to find out the particular solution for this non-homogeneous equation. We will start with the basics. So, let us first find out that is basic technique to solve the non-homogeneous equation. It is method to find yp. Let us start with the, as I said, is with basics. So, let us start with an example. Find the general solution of y double dash plus 3y dash plus 2y is equal to 12 times e to the power x. We see this is a linear equation, its coefficients are constants, but the right hand side is not 0, that is it is non-homogeneous. So, what we do is first we will solve the associated homogeneous equation. What is the corresponding homogeneous equation? Y double dash plus 3y dash plus 2y is equal to 0. We do know how to solve it. First we find out the characteristic equation. What is the characteristic equation? Lambda square plus 3 lambda plus 2 is equal to 0. What are its roots? Of course, it is lambda plus 2 into lambda plus 1 is equal to 0. So, it has two roots, minus 1 and minus 2. They are distinct real numbers. So, what will be the corresponding general solution of the homogeneous equation? That will be C1 e to the power minus x plus C2 e to the power minus 2x. Now, the differential equation was y double dash plus 3y dash plus 2y is equal to 12 times e to the power x. Now, I have to find out the particular solution. Particular solution means is that is it should be a solution of this equation. Now, let us see, right hand side we are having the term e to the power x. So, now if I experiment with e to the power x, we do know its derivative as well as double derivative all are e to the power x. So, if I am substituting, so we can try like this one. So, what we are doing is we are taking particular solution as a times e to the power x, because I do not know what will satisfy this equation. That means, it should, if I am putting e to the power x, I should get equal to 12 times e to the power x. So, I have taken that as a constant, because e to the power x I can obtain by putting e to the power x, but this constant we have to obtain. So, I have put here a. How to obtain this a? Now, if I am assuming that this is a solution, this must satisfy this equation. So, now I will substitute yp dash and yp double dash in this equation. So, what is yp dash? A times e to the power x, and yp double dash, that is again a e times e to the power x. Let us substitute it. We would be getting is a times e to the power x into 1 plus 3 plus 2 is equal to 12 times e to the power x. What it says that 6 a times e to the power x is equal to 12 times e to the power x, which implies that my a must be 2. That is, the particular solution should be 2 times e to the power x. We can check that this is satisfying this equation. So, this is a particular solution. So, now what will be the general solution of our non-homogeneous equation? That would be the general solution of homogeneous plus the particular solution. So, I get C1 e to the power minus x plus C2 e to the power minus 2x plus 2 times e to the power x. So, this is the general solution of homogeneous equation. We can check that if I substitute this function and its derivatives in this equation for any value of C1 and C2, that is, take the general constant C1 and C2, I will obtain, that is, this will satisfy this equation. So, this is the general solution of the non-homogeneous equation. So, this is here we have done with an example, and the basic instinct we have got, that is right hand side we had seen that it is containing the term e to the power x, and we had already experimented from the beginning of this course with the function e to the power x. So, we could do it. Now, let us learn the methods to find out yp. We will learn here the two methods to find out this particular solution. The one method of undetermined coefficient, that is something like that what we have done in this example, and there is another method called method of variation of parameter. So, first we will learn the method of undetermined coefficients. What this method says is, this method is, first let us learn that is where this method is applicable. This method is applicable in the equations with constant coefficients. So, see, we would be dealing with only linear equations with constant coefficients, and right hand side R x, that is also of a special form. That special form, that is either my R x is of the form e to the power a x, or it is a polynomial, or it may be a function of cosine or sine, something like that, then only this method is applicable. Now, let us learn what this method is. This method says is that if R x is of a special form, I would choose that particular kind of yp. How we are doing it? Let me summarize it by a table. We say that is, if I do have the R x as k times e to the power gamma x, that as in our example I was having 12 times e to the power x, that is gamma was 1. And what I have chosen? I have chosen the yp as e to the power x and a here. That says is that if R x has of the form k times e to the power gamma x, choose yp as c times e to the power gamma x. If my R x is containing the polynomials, that is here I have given the example as k times x to the power n, then choice of yp will be a polynomial of degree n. See here, we are not taking only k times x to the power n, we are taking the complete polynomial k naught, k1 x plus so on kn x to the power n. So, if it is a polynomial or if it is some terms of polynomial, in the choice of yp we will always choose the complete polynomial of degree n. Then, if the terms in R x are cosine or sine, that is k times cosine omega x or k times cosine sine omega x, we would choose yp as a sine omega x plus b cosine omega x. Again you see, my R x may contain only cosine or only sine, but in the yp we would choose both sine and cosine function. Now, if the term in the R x is having a multiple of e to the power alpha x and cosine or sine terms, we would be choosing yp as e to the power alpha x, a sine omega x plus b cosine omega x. That is Now, what are the rules to apply this method? So, we will learn some basic rules. Rules of this method are, first is called the basic rule. Basic rule just now as I had explained you, that is for second order linear differential equation which is non-homogeneous, y double dash plus p x y dash plus q x y is equal to r x. If r x is one of the function in the first column of the table, just now as I had explained, I would choose corresponding function y p in the second column and find the value of undetermined coefficient by putting y p and its derivative in the given equation. So, we had got, that is, by using that table we can choose y p, and as in our example what we have done, we had find out the value of a by putting y p dash and y p double dash in the equation, and then we have determined what is a. So, here whatever the undetermined coefficients k, c, k1, k0 and so on, we could find out all of them by putting y p and its derivatives in the non-homogeneous given differential equation and solve for the unknown coefficients. That is why it is called the method of undetermined coefficients. Now, you do remember I said that the general solution contains two things. One is general solution of associated homogeneous equation y h x and another is y p x. Now, it would be the general solution that says is I should have y p also linearly independent of the solutions which we are having as y 1 and y 2 of the homogeneous equation. That says sometimes it may happen, that is whatever I am getting as the choice of y p, that may turn out to be one of the solution of the homogeneous equation. Then of course, because here I am choosing it a constant time, that function, that will not be linearly independent of the solutions of homogeneous one. So, how to solve this kind of problem? That says is the second rule as modification rule. It says if any term in the choice for y p is also in the solution y h of corresponding homogeneous equation y double dash plus p x y dash plus q x y is equal to 0, then multiply the choice y p by x or by x square if the solution corresponds to the double root of the characteristic equation of the homogeneous equation. Why we are doing it? Say we can understand this very well. Since that particular solution is also coming as in the solution of homogeneous equation. So, with a constant coefficient, of course, we cannot get it as linearly independent. So, we have to multiply with x. Now, if it is solution corresponding to the double root, then we do know that x times that solution is also coming as the fundamental solution. So, I have to multiply it by x square. Then there is one more rule, that is called sum rule. What it says is I may have r x, that is r x is sum of different functions given in the column 1 of the table. Then choose y p as the sum of corresponding functions in the second column. Now, let us see that is how to use these rules and how to use this particular method to find out the general solution of non-homogeneous equation, that we will see through some examples. So, let us go with the examples. First example, let us say solve the non-homogeneous equation y double dash plus 4 y is equal to 8 x square. We see this is a second order equation, constant coefficients are constants, and right hand side is of the special form, that is it is a polynomial, that is 8 times x to the power 2. So, go for the solution. Given equation is y double dash plus 4 y is equal to 8 x square. The corresponding homogeneous equation will be y double dash plus 4 y is equal to 0. To solve this, we require the characteristic equation. What is the characteristic equation? That is lambda square plus 4 is equal to 0. What will be its root? It is lambda square is equal to minus 4, that means it will have complex conjugate roots. The roots would be plus minus 2i. We do know in this case what is the general solution of homogeneous equation, that is C1 cosine 2x plus C2 sin 2x. Now, what is my right hand side? That is 8x square. Now, if you are not remembering, we of course go back to our table. We are having 8x square, that is here n is equal to 2. So, what we would choose? We would choose k naught plus k1x plus k2x square. So, let us see. Since Rx is 8x square, Yp we would choose k2x square plus k1x plus k naught. Now, substitute its derivatives in the equation, that is first find out what is Yp dash, that is 2k2x plus k1, Yp double dash would be 2k2. Now, substitute this in the given equation, y double dash plus 4y is equal to 8x square. What we get? We get 2k2 plus k2 square 4k2x x square plus 4k1x plus 4k naught is equal to 8x square. Now, to find out these constants, we will compare the coefficients of different powers. So, equating the coefficients, we get the coefficient of x square on the right hand side is 8, while the coefficient of x square on the left hand side is 4k2. So, the first equation we are getting is 4k2 is equal to 8. Then we are getting is the right hand side, the coefficient of x is 0, while on the left hand side the coefficient of x is 4k1. So, I get 4k1 is equal to 0. Now, right hand side I do not have any constant term, while on the left hand side I do have the constant term 2k2 plus 4k naught, that says is 2k2 plus 4k naught is also 0. Now, from the first equation I am getting k2 is equal to 2, second equation gives k1 as 0, and the first equation and the third equation gives me that k naught is equal to minus 1. Now, substitute this in our choice of Yp. What I would get? I would get Yp as 2x square minus 1. So, what will be the general solution of our equation? Y double dash plus 4y is equal to 8x square, that is C1 cosine 2x plus C2 sin 2x, that is the general solution of homogeneous equation, plus this particular solution 2x square minus 1. Now, you can again check with this solution, find out its derivative and second derivative, substitute in this equation and check, that is in general if I am taking only C1 and C2, this will satisfy for all values of C1 and C2. So, these would be the interesting exercises for you to do. You can check it that this is a solution of this non-homogeneous equation. Now, let us do one more example. Yeah, one more thing here. You would be worrying, that is why I have chosen this, as I said is we will always choose polynomial. You can try one more interesting exercise. You can try only with kx square, do not choose the complete polynomial, and see that what the solution you are getting, that will not be actually a solution of this non-homogeneous equation. There is another interesting exercise which you can try. So, let us move to the second example. Solve the initial value problem, y double dash plus 2y dash plus y is equal to e to the power minus x, where the initial conditions are that the function at 0 is minus 1 and the derivative at 0 is 1. Move to the solution. The given differential equation is y double dash plus 2y dash plus y is equal to e to the power minus x. See again, we are having the equation has constant coefficients and right hand side is of a special form e to the power minus x. First find out the corresponding homogeneous equation, that is y double dash plus 2y dash plus y is equal to 0. For solving this, we require its associated characteristic equation, that is lambda square plus 2 lambda plus 1 is equal to 0. We see this is the whole square of lambda plus 1, that is we are going to get the double root lambda as minus 1 and minus 1. We do know in homogeneous equations, when we are having the double root, the solution is e to the power minus x and the other solution we choose x times e to the power minus x. So, the general solution would be C1 plus C2 x times e to the power minus x. Now, right hand side is e to the power minus x. Now, you see if I am using our table, I would get yp as a times e to the power minus x or c times e to the power minus x, but this e to the power minus x is also coming as here in the e to the power minus x is also a solution of my homogeneous equation. Moreover, this is a solution corresponding to the double root, that is x times e to the power minus x is also a solution. So, we have to apply the modification rule. So, again I am repeating these steps. First we see from our table, since I do have e to the power minus x, I would choose c times e to the power minus x, that is gamma is minus 1. Since again this e to the power minus x is coming as a solution of the homogeneous linear equation, we do apply the modification rule. The modification rule says is multiply the choice of yp by x or by x square. So, here my solution e to the power minus x is corresponding to the double root. So, I have to multiply by x square. That says is I should choose my yp as a times x square times e to the power minus x. Find out what is yp dash and yp double dash. So, yp dash, its derivative 2 a x e to the power minus x minus a x square e to the power minus x. Second derivative 2 a e to the power minus x minus 2 a x e to the power minus x minus 2 a x e to the power minus x plus a x square times e to the power minus x, that is it will be 2 a e to the power minus x minus 4 a x times e to the power minus x and plus a x square e to the power minus x. Substitute this in given equation, that is y double dash plus 2 y dash plus y is equal to e to the power minus x. Left hand side what we would be getting 2 a e to the power minus x minus 4 a x times e to the power minus x plus a x square e to the power minus x plus 2 times its derivative, that is we are getting it as 2 a x e to the power minus x minus a x square e to the power minus x plus y is 8 x square e to the power minus x. This must be equal to e to the power minus x. Let us see in the left hand side. Here I am having is minus 4 a x e to the power minus x. This would be plus 4 a x e to the power minus x, that is this term is get cancelled out. Here I am getting is a times x square e to the power minus x, that is coefficient of x square e to the power minus x. Here is a, here is minus 2 a since this 2 and here is one more a plus a, again it is cancelling out. So, what is being left? I have been left with 2 a e to the power minus x is equal to e to the power minus x. So, comparing the coefficients we get 2 a is equal to 1 or a is equal to half. So, what will be my yp? Yp would be half x square e to the power minus x. So, the general solution would be C1 plus C2 x e to the power minus x, that is the general solution of homogeneous equation, plus this particular solution half x square e to the power minus x. Now, you can actually again check with this solution that you could find it out, that substitute these in this equation and find out that this is satisfying this equation. And moreover, here we are getting is e to the power minus x, x times e to the power minus x and x square e to the power minus x, all of them are linearly independent. Now, to find out the particular solution, because this is an initial value problem which we had started. So, for finding out the particular solution, what are the initial conditions we have been given? We have been given that the function at 0 is minus 1 and its derivative at 0 is 1. What the general solution we had got? C1 plus C2 x e to the power minus x plus half x square e to the power minus x. Now, if I substitute this function at x as 0, that is I find out the value of the function at 0, that is given as minus 1. From here in this solution, if I am substituting x as 0, I would get only C1. So, it gives C1 is equal to minus 1. Then find out its derivative. Derivative is minus C1 plus C2 x e to the power minus x minus half x square e to the power minus x plus C2 times e to the power minus x plus x times e to the power minus x. Now, again the second condition is y dash at 0 is 1. So, again we are putting x is equal to 0. What I would be left? I would be left minus C1 plus C2 which is equal to 1. From the first result we have got C1 as minus 1, that gives C2 as 0. So, we have got the particular solution, that is I will put C1 is equal to minus 1 and C2 is equal to 0 in our general solution of homogeneous equation. So, I would get the solution of initial value problem as minus e to the power minus x plus half x square e to the power minus x. We can check that this is satisfying both initial conditions, that is the function value at 0 is minus 1 and the function derivative of the function at 0 is plus 1. Let us do one more example over here. Find the general solution of y double dash minus 3 y dash plus y double dash minus 3 y dash minus 4 y is equal to 3 times e to the power 2 x plus 2 times sin x minus 8 times e to the power minus x. Now, we see our right hand side is actually sum of many functions which are in our table, e to the power 2 x, e to the power minus x, sin x and so on. So, it says is that we have to use the sum rule. Let us see if we have to use some other rules also. So, first we go for the solution. What is the corresponding homogeneous equation? Y double dash minus 3 y dash minus 4 y is equal to 0. To solve this, we require the characteristic equation. What is the characteristic equation? Lambda square minus 3 lambda minus 4 is equal to 0. We do find it out that it is nothing but lambda minus 4 into lambda plus 1, the factors. So, it will have 2 roots minus 1 and 4, they are real and distinct. So, the general solution of homogeneous equation will be C1 e to the power minus x plus C2 e to the power 4 x. Now, we see right hand side. Right hand side R x we have 3 times e to the power 2 x, 2 sin x minus 8 times e to the power minus x. Now, so if I just go with our table, if you do remember something, that is e to the power gamma x, we do take c times e to the power gamma x. So, here if I do take, I have to choose one y p as e to the power minus x, and that is here again as a solution corresponding to the one root. That means, we have to use the modification rule, that is in this one we would be going to use the sum rule as well as the modification rule. For the sum rule, we require which functions we have to choose. We have here function of e to the power gamma x and sin x. So, let us consult our table. E to the power gamma x means I have to use constant times e to the power gamma x, and sin omega x I have to use the function which is having a constant times sin omega x and a constant times cosine omega x with plus. So, let us see what will be our choice of y p. The choice of y p would be a times e to the power 2 x plus b 1 sin x plus b 2 cos x plus dx times e to the power minus x. Why I had chosen here it? Since e to the power minus x was already a solution. So, I have to modify it as x times e to the power minus x. So, here I had used the modification rule, and in this complete one I had used the sum rule. So, we have got this as the choice of y p. Now, find out its derivative. 2a e to the power 2 x plus b 1 cosine x minus b 2 sin x minus dx e to the power minus x plus d times e to the power minus x. Second derivative 4a e to the power 2 x minus b 1 sin x, derivative of sin x is cosine x. So, b 2 cosine x, derivative of dx e to the power minus x is plus dx e to the power minus x minus d e to the power minus x, and the derivative of this is minus d to the power minus x. Now, substitute this in the given equation. What was the equation? Equation was y double dash minus 3 y dash minus 4 y is equal to 3 times e to the power 2 x plus 2 sin x minus 8 times e to the power minus x. So, substituting it, and of course, the calculations you can check it, we get minus 6 a times e to the power 2 x minus 5 b 1 minus 3 b 2 sin x minus 5 b 2 plus 3 b 1 cosine x minus 5 d e to the power minus x. This should be equal to the right hand side, that is 3 times e to the power 2x plus 2 times sin x minus 8 times e to the power minus x. Now, equate the coefficients, we get the coefficient of, here you see e to the power 2x, its coefficient here is minus 6a, here is 3. So, I would be equating this as this one. The coefficient of sin x here is minus 5 b 1 minus 3 b 2 and here is plus 2. So, I would get 5 b 1 minus 3 b 2 is equal to minus 2. The cosine x term we do not have over here. So, this 5 b 2 plus 3 b 1 would be 0. The coefficient of e to the power minus x is minus 5 d here, here it is minus 8. So, I would get 5 d is equal to 8. So, equating the coefficient I am getting minus 6 a is equal to 3, which gives me a is equal to minus half. Second, what we are getting for cosine and sine, 5 b 1 minus 3 b 2 is equal to minus 2 and 5 b 2 plus 3 b 1 is equal to 0. Solving these equations, we get b 1 as minus 5 by 17 and b 2 as 3 by 17. And last one we are getting 5 d is equal to 8, gives me d is equal to 8 by 5. So, what will be our particular solution? Substitute these a, b, 1, b 2 and d. Minus half e to the power 2x minus 5 by 17 sin x plus 3 by 17 cosine x plus 8 by 5 times x into e to the power minus x. So, the general solution would be, this is the general solution of homogeneous equation C 1 e to the power minus x plus C 2 e to the power 4 x. There is this particular solution, that is same thing I have written here and of course, we get is, that is, since here it is e to the power minus x, here I am getting is x times e to the power minus x. So, now this is what is the general solution of this homogeneous equation, where now we had used all the 3 rules, that is we have seen the basic rule, then we have seen the modification rule, we had used the sum rule also. Now, we will learn the second method of finding the particular solution, that is method of variation of parameters. This method is more general, it does not require any special conditions on your equation, neither it requires any condition on your right hand side R x. It is more general, but little bit more complicated. Let us see what this method says is, that is may have p x q x as any, there is no special assumptions on this. How this method is working, or what is this method? Let us say a non-homogeneous equation y double dash plus p x y dash plus q x y is equal to r x, where I do have that p x, q x and r x are arbitrary, but continuous only. That is, we require the condition only that these coefficients on the right hand side has to be continuous on some interval I. We also require to know the basis solutions of the corresponding homogeneous equation. So, associated homogeneous equation y double dash plus p x y dash plus q x y is equal to 0. Let us say that is the fundamental set of system, or the basis of solution is y 1 and y 2. Then how we are finding the particular solution? This would be the general solution of homogeneous equation. The particular solution we are saying is another function as u 1 y 1 plus u 2 y 2. That is, we had obtained corresponding homogeneous equation, its general solution. Then for particular solution we had chosen u 1 y 1 plus u 2 y 2, where this u 1 x and u 2 x are any arbitrary functions of x only, continuous and differentiable. How to obtain this u 1 and u 2? For this what we are doing is, we are substituting this yp dash and yp double dash in this given equation. So, when we substitute it, we do use this condition also, that is y 1 and y 2 is the solution of corresponding homogeneous equation. All those things when we do, we can find out this u 1 u 2 as the solution of the system of this system, that is u 1 dash y 1 plus u 2 dash y 2 is equal to 0, u 1 dash y 1 dash plus u 2 dash y 2 dash is equal to r x. You see, here I am getting the two equations which are having y 1 dash, y 2 and y 2 dash, but they are both are having u 1 dash and u 2 dash. That is, I would get the solution of this system of linear equations as the u1 dash and u2 dash, and then u1 and u2 we can obtain as integral of them. So, what will be that solution? Let us see here. u1x is minus integral y2x rx upon Wronskian of y1 y2. W of y1 y2 is the Wronskian of the solution y1 and y2. y1 y2 are the general solution, the fundamental set of solution of associated homogeneous equation. This integrated with respect to x, and u2 is y1x rx upon Wronskian of y1 y2 integrated upon with respect to x. These are the two solutions. So, what I will get the particular solution? We would get, so here this is being written that Wronskian of wy1 y2 is the Wronskian of the fundamental solutions y1 and y2. yp we would get minus, that is u1 y1. So, minus y1 integral y2 rx upon Wronskian of y1 and y2 plus y2 times integral y1 rx upon Wronskian of y1 by 2 integrated with respect to x. You see here that we are now, there we had learned the Wronskian, and we said is we are using it for showing the linear independence of the solution. Now, you find it out, if they are linearly independent, we do know that this Wronskian cannot be 0. Since it cannot be 0, so in the division it will not create any problem, and we are seeing now here that is how we are using Wronskian to find out the particular solution of non-homogeneous equation. Let us try to learn that how to use this method. So, let us learn with one example. Find the general solution of y double dash minus 4y dash plus 4y is equal to e to the power 2x upon x. You see, of course, we do not require any special conditions on the coefficients of the differential equation, but since till now we had learned only to find out the solution of linear differential equations with constant coefficients. So, in this example I have taken this coefficients to be constant, but the right hand side is not of the form in which I could use the undetermined coefficient, that is method of undetermined coefficient, since what I am having the right hand side e to the power 2x upon x. Now, it is not coming as the sum of any known functions, because it is the ratio of two functions which are in that table. So, I cannot use that method. So, I do not have any option other than to use this method of variation of parameter. So, let us try to solve this. First, we will find out associated homogeneous equation, that is y double dash minus 4y dash plus 4y is equal to 0. To solve it, we require the characteristic equation, that will be lambda square minus 4 lambda plus 4 is equal to 0. Now, we see this is nothing but lambda minus 2 whole square, that is again we are getting the double root lambda is equal to 2 and 2. What will be the general solution of this, or what will be the fundamental set of solutions? The fundamental set of solutions would be e to the power 2x and x times e to the power 2x. Now, so what should be the Wronskian of this fundamental solutions? That is, I have got two solutions, e to the power 2x and x times e to the power 2x. So, Wronskian first row is as such, second row the derivative, that is 2 times e to the power 2x, 2x times e to the power 2x plus e to the power 2x. When we solve this determinant, we get, since here we would be getting is 2x e to the power 4x plus e to the power 4x minus 2 times x times e to the power 4x, I would get e to the power 4x, which is not 0. Since these are linearly independent, I am getting this is not 0 for any value of x. So, we have got e to the power 4x as the Wronskian. So, what will be now my u1 and u2, rather than using that putting u1 y1 in those ones and finding out what it is, we would be using the formulas directly. YH is c1 e to the power 2x plus c2 x times e to the power 2x. For yp, rx is e to the power 2x upon x. So, now what will be my u1? The formula says minus integral y2 x rx upon Wronskian of y1 y2 integrated with respect to x. Substitute this values of y2 rx and so on. y2 is x e to the power 2x, Rx is e to the power 2x upon x, Wronskian wy1 y2 is e to the power 4x. Let us substitute x e to the power 2x into e to the power 2x upon e to the power 4x. We are getting is that this x is being cancelled out by this, e to the power 4x is being cancelled out with this. I am getting is integral dx, that is a constant with respect to x, I would get minus x. So, u1 I have got minus x. What will be u2? u2 is y1x Rx Wronskian of y1 y2 integrated with respect to x. y1 is e to the power 2x, Rx is e to the power 2x upon x, Wronskian is e to the power 4x. What I am getting is e to the power 4x is cancelling out, I would be getting integral of 1 by x dx, which we do know is log x. So, what will be my particular solution? u1 y1 plus u2 y2. u1 we have got minus x, and what was y1? E to the power 2x. So, minus x e to the power 2x, u2 is x times e to the power 2x, y2 we have got log x. So, we are getting log x times x e to the power 2x. So, what will be the general solution? General solution would be c1 e to the power 2x plus c2 x times e to the power 2x minus x times e to the power 2x plus x log x e to the power 2x. Now, we can rewrite it because we are having e to the power 2x all the places. So, we can rewrite it as c1 plus c2 minus 1 plus log x whole multiplied with x, then whole multiplied with e to the power 2x. So, this is what is now here we have learned one method which says is method of variation of parameter, how we are obtaining the particular solution when the right hand side is not of the special form and we are not getting that as from the undetermined coefficients. Of course, we have learned only about differential equations which have constant coefficients. Now, this is what all about we had learned about linear differential equations with constant coefficients. Homogeneous equations we had learned how to solve them, we had learned about non-homogeneous equations as well, where we had learned that is all the methods which we had learned in the non-homogeneous equations, they were applicable both with whether the coefficients are constant or the coefficients are not constant, they are general functions, they are not changing, but all the examples which we had done, they were having all the coefficients as constants. Why? Since we had learned in the linear differential equations only to solve the constant coefficients, that is why in the non-homogeneous we could not do any example where the coefficients are not constants. So, next lecture we would learn about the linear differential equations which have the coefficients as non-constant, that is my p x and q x are functions rather than the constants. So, that is all for the today's lecture. Thank you for this.